Ok, gracias. So, okay, guys, I'm sorry again because I'm speaking in English. I cannot do that in Spanish. Feel free to stop me whenever you want, ask some question, or ask me to rephrase if because my English is also with a very, very strong French accent. So I'm sorry for that. And you can ask me a question when you want, and feel free to ask also in Spanish, in your language. So it's fine. So I'm going to talk about ocean-atmosphere interaction at mesoscale and why it matters, and what are the main implications for ocean dynamics, but also for atmospheric dynamics. So we know that ocean models are strongly constrained by atmospheric forcing, right? So when you do your CROCO experiment, you do make forcing. So what an ocean model needs to run? Can you guess like the three question mark that I want here? So the ocean model is forced. What winds? Okay, winds is one. Heat fluxes. Okay, heat fluxes might be separated into turbulent heat fluxes, so sensible and latent heat flux, but also radiation, right? So winds, heat fluxes, and a third one? Tides. No, let's say like a tides, well, it's a forcing as well, you're right, but you can run an ocean model without tides, okay? Like ocean tides. No, because you can run an ocean model without tides. So it's not mandatory. But the third one is, no clue, pressure, okay. Well, let's say like this is not the thing that I expected, but freshwater flux, right? So evaporation and precipitation. Okay, so winds, heat fluxes, and freshwater fluxes. So in this training, so far you use those forcing or an atmosphere or these atmospheric variables as prescribed, okay? This is totally fine, but in that case, we see the ocean that respond to that forcing, but not the feedback to the atmosphere and the two-way feedbacks, right? This approach is very, very appropriate for many, many studies, right? So it depends of your scientific question. But as I said, like depending on your scientific question, like neglecting some processes involved like RC interaction might lead to bias or incomplete results, okay? Why? Is because we know that many processes coexist, okay, over a large spectrum of temporal and spatial scales between like atmosphere and ocean. And those interaction may be like key features really like for the dynamic of the atmosphere or ocean and ocean. Today I'm mostly going to talk about interaction at mesoscale, okay? And we're going to see how the atmosphere control the upper ocean variability, and how, at the contrary, the ocean temporal variability can control the surface, the boundary layer of the atmosphere. And we're going to see also some upscaling effects, which means that, okay, these processes like act at mesoscales, but have influence on a larger scale of dynamics. So just a very, very simple sketch here to mention that there is three main feedback loops at the interface, okay? If we consider like a boundary layer of the ocean and boundary layer of the atmosphere as a continuum, we have three main feedback loops, which is a mechanical feedback loop, okay? So how the wind and the current are connected to set the stress, which is actually the main forcing for the ocean, right? The wave feedback, which controls the roughness of the sea, and the thermal feedback, so how the sea surface temperature structure control some atmospheric variable, which is heat fluxes, wind, atmospheric stability, flux of humidity, and all those processes are very important for clouds and rain. And if we mention clouds and rain, that means that it's very important for radiation and heat budget in general of the system, right? So today I'm going to talk mainly on the thermal feedback and current feedback, right? We're not going to talk about waves. So this is like the content of that talk. So we're going to start with the thermal feedback, okay? I'm going to give you an example of an important processes. What is the atmospheric response to that? Some upscaling effect, and well, I'm going to conclude as well. Current feedback, so also I'm going to explain the basic concept, the effect for ocean dynamics, the effect from atmospheric dynamics. And I'm going to conclude to say what to do with this info and conclude with some strategy in model and simulation, right? Okay, so let's go with thermal feedback. We know that when wind is blowing over the sea, okay, that creates a motion in the ocean, which generates mixing, right? So on a large scale, if we think about like wind and the response of SST, the more powerful the wind, the colder the SST, right? Because that's make like a mixing. So if we calculate a simple correlation between wind speed and sea surface temperature, more powerful the wind, colder the SST. So the correlation is negative, right? So this is true, this is here, for many parts of the world, okay, or the world ocean, at large scale, okay? Now if we remove the large scale and we just take the SST, the mesoscale, sorry, of the wind and the sea surface temperature, and we do that exercise again, so we compute the correlation, this is the result, okay? So we see that positive correlation emerge. That means that some ocean and SST features at mesoscale, the warmer the SST, the stronger the wind response at mesoscale. Okay, so the ocean actually drive the atmosphere. Okay, so let's dig into why this positive correlation like appears. And here we call that, so this is a specific process called downward momentum mechanism. So practically, the eddies in the front of the ocean alter the stability of the marine boundary layer, so the atmospheric boundary layer above the sea. And that activates some turbulent fluctuation of the momentum from the top of the atmospheric boundary layer to the surface layer, to the sea. And actually, this process has been observed and also modelized. So here is, for example, radiosonde observation in the Eastern Pacific. What we see, actually, the boat goes from, well, there to there, and there are some radiosondings. And this is the SST along the boat track, right? And here, this is the radiosondings of the atmosphere. And what we see is like at the cold core of SST, mesoscale SST, we have a reduction of the mabel height, okay? So the boundary layer actually reduced. And we have way more shear in the wind, okay? At the contrary, on the warm flank, we have an expansion of the mabel height, of the mabel, and a very uniform winds, Okay, so here it's sketched exactly the same. If we go from warm to cold SST, here we have an unstable atmospheric boundary layer with an increased mixing. And here we stabilized, actually, the atmospheric boundary layer. That's go down, and there is like less mixing. Okay? Okay, what does that imply? That implies like here, if my first arrow is surface winds, so winds at 10 meter height, there is stronger wind over the warm side of the front, and so less wind on the cold part of the front. So here, what we can guess, here we have convergence, right, of the wind. And here we have an SST gradient. So to highlight that process, we're going to relate SST gradient, which is the difference of the SST there, to convergence or divergence of the wind. Okay? So if we pass from, if the wind blows from warm to cold, okay, we have a positive SST gradient, well, the wind, negative, sorry, SST gradient, so we lose some temperature, and the creation of convergence, okay? And obviously, so this is what is happening at the surface, but that convergence means upward movement and creation of clouds, okay? So this is exactly what we do. So we related SST gradient with wind divergence, okay? And actually, if we plot that like everywhere on the global ocean, we have actually this plot, which means that we can related SST gradient for wind divergence at the surface, okay? And this relation is quite linear, so quite simple, okay? So the slope of that linear function is calling the coupling coefficient, okay? So how the atmosphere responds to the SST gradient. This is, so it's in almost a linear way. So the first question is like, for which like environmental condition that these processes depends upon. Okay, so we're going to do that exercise several times with different conditions. And here I propose condition with the wind speed and condition with stability. Okay, and the proxy for stability is the difference of temperature between atmosphere and ocean. What we see is like, okay, so the red line here and here is exactly the same as the previous one. Okay, this is all condition. On the green, for example, I just did this scatter plot for only winds slower than 5 meters per second. And the violet one is actually wind greater than 12 meters per second, which is like kind of a strong wind. And what we see is like the stronger the wind, the stronger the slope. So the stronger is actually the creation of this wind divergence response to SST gradient. Here, we do the same thing with the RC temperature difference. And what we see is like we see that if the RC difference is very, very small, so kind of near neutral atmospheric stability, that increase this coupling coefficient, okay? So we can generalize that, that result for all type of background condition. Here, if we take the information only on the slope, we have only one number, right? So this is the slope of that format. And this is a generalization. So in colors, this is the slope, okay? The darker red, reddish, is the more efficient the coupling coefficient, the coupling process, okay? On the x-axis, we have RC temperature difference, okay? So that's all the range that I have, and background wind speed. And what we see is like, well, the cross means that is not statistically significant, okay? But everywhere, the color means that the DMM, so the downward momentum mixing, is acting everywhere, well, with all type of condition, but more pronounced for a slight stable condition, well, neutral condition, and for higher wind speed. Okay, so this is the surface response, so the wind divergence and convergence structure response to SST gradient, but really at the surface, so 10 meters, okay? So now we can wonder what is happening higher in the air column, okay? So here I propose to travel a bit in the Mediterranean Sea, and we're gonna do same kind of exercise. Here I show you the correlation between SST gradient and the wind divergence, okay? You remember for the global map, if it's red, means that the DMM acts, okay? This process is acting. So we are happy, we verified that this is true for the surface. And we're gonna compute all those correlation with different level of wind from different level higher in the atmosphere. And we see that the correlation here is positive, so that means that the DMM is acting up to 925 hectopascal in the atmosphere, okay? And here we cross the zero. And here is actually the mean height of the atmospheric boundary layer. And then we start to have like non-significant zero correlation. So we agree with that result show that there is an agreement with the theory saying that the downward momentum mixing is actually acting on all the atmospheric boundary layer. Okay? So what does that imply for clouds and rain? Once again, you remember, so if I'm the wind, I'm going from warm to cold. That means that here, at the level of the front, there is a convergence. So there is an upward movement and possible creation of clouds and rain. And this is actually true. Okay, so this is when the SST is going to the cold side, okay, and to the warm side. So here you have a creation of convergence, and here a creation of divergence, okay? So this is my SST gradient percentile, okay? So this is like my maximum front to the warm side is there, my maximum front to the cold side is there. And what we see is still over the Mediterranean, is my cloud cover, my relative, on the left is the relative change in cloud cover, and on the right is the relative change in rain event. And what we see is like when we have this process acting the most, we have more chance to have a cloud, okay, over warm to cold SST gradient, and clear sky when we go from cold to warm. And we have more chance to have rain, and relatively less chance to have rain, according to that processes. Okay, so far we've seen that SST gradient actually have a surface response in wind, also responses in the whole air column until the top of the atmospheric boundary layer, but it's still like a local response, okay? So this response is really like on top of an SST gradient. Now we can actually ask some question. What is like the some upscaling effects in the atmosphere. So if we're taking into account, okay, what is the relative change? And I did that over Southern Africa. So here to respond to that question, so what is, if we take into that account into a model, what is actually the atmospheric response? So here, we are in Southern Africa, and we are interested into, well, summer climate. And summer climate, one of the most important things is, well, which is the rainy season, right? Is this low pressure system there at the border of Angola and Namibia. On the black line here is my domain of my atmospheric model, okay, WRF, which is the equivalent of CROCO, but for the atmosphere. And I'm going to force that model. Well, this atmosphere gonna see either the full spectrum of SST there, or only the large scale, okay? And we're gonna make the difference. And actually, so this is like the control run. We are happy because we have these big low pressure guys, and the dots in violet here are the clouds. Here is the mean difference in the representation of this atmospheric low pressure system. Okay? And here you have a time series. And if we force our atmospheric model with a full spectrum of SST, so means that the downward momentum mechanism act, we have actually a deeper low. Okay? Why is it interesting? It is interesting because so far we've seen that it's very important for local, atmospheric local thing. But we see that leads to a difference even over land. Why? Is because we change our atmosphere and wave and baroclinicity, okay? And that results in a very, very different mean precipitation over the summer, okay? So here you have colors like for more precipitation per day or less precipitation per day, okay? And this is in milliliter per day, but well, roughly this is correspond to 20% of the rain, and here up to 25%, okay? So that means that this coupled thing act also on larger scale and can modify the atmospheric main distribution, okay? Well, here we are in Southern Africa, but in Southern America, it works the same because this is a very typical interaction between tropics and extratropics. So you also, guys, have some like low pressure system and make the rain in a diagonal way, right, over Southern America. Okay. Take-home message on thermal feedback. So we see that if the atmosphere encounters some fronts and SST gradient, we have two kinds of responses. So warm to cold, making some converging winds that excite upper motion, enhance cloud formation, and increase the chance of rainfall. On the contrary, if we go to cold to warm, we have diverging cells, downward motion, so cloud-free sky, and a decreased chance of rainfall. This process acts on a larger scale atmospheric response. So we saw that for the Southern Africa summer climate, okay? And something that I didn't show, but there is some also ocean response, obviously, because here we impact the heat fluxes because we modify the wind, and the influxes is also a function of the wind and the SST, right? Yes. So last point on that is this is true at mesoscale, but this is also true at sub-mesoscale. That involves like different processes, and it's a bit more complicated, but this is true. Okay. let's talk about current feedback now. So we've seen the thermal feedback. So now is a mechanical feedback between the ocean and the sea, which called like a current feedback. So yeah, yes, sure.
If I understood well, the coping coefficient is larger if the temperature, there's no temperature difference between air and sea?
Yes, when it's like a neutral stability.
Same temperature?
Yes, yes. Which is quite rare though, but okay. It happens. So that means that yes, I mean, if the difference is large, either you are like super stable. So that means that the ocean has less influence. Either you are like super unstable, and that means like it's all mixing process. So it works as well.
At what time scale do you calculate that?
From a sub-daily to monthly seasonal. So it's very quick, actually. The atmospheric response is very fast. Okay. So mechanical feedback, okay? You all know that the transfer of momentum between the atmosphere and the ocean is given by the stress, okay? Here, this is a classical definition of the stress is actually, raw atmosphere, CD, which is a drag coefficient, right? And a function of U square, okay? For a long time, we took that U as the wind, okay? But actually here, we're gonna use the relative motion between the two fluids. So U rel is for U relative, and U relative is actually the wind speed minus the surface current, okay? So that means that the surface current gonna appear in the computation of the stress. Here, note that we do not change the CD, which is still highly non-linear with the relative wind. So here, some concept. If we want to know actually the effect of that current feedback. Here some basic concepts to show you what is the meaning of taking account or not the ocean current. So here we have a sketch with the green arrow is representing the wind. Okay, so it's very homogenized. The black arrow is the stress, and here a cycle is actually an eddy. Okay, is an eddy in the ocean. If we do not take account the U ocean in the stress formula, we have this kind of response. So here, well, first we're gonna calculate the wind work. Okay, so this is like the work in the physical sense exerted by the wind. Okay, over the ocean. So here, what we see is like if there is like an eddy, even a strong eddy, that do not interact with the calculation of the stress. Okay, so the stress and the wind are not moving. Okay, it's still homogenized. The wind work is then 0. Here, if we take into account this ocean current, what we do have is like we have more stress when the current is opposite to the wind, and less stress when the current and the wind are aligned. Okay? So if we compute our wind work, here we have a negative wind work. Okay, so this is a calculation on the stress. But then, obviously, if there is more stress, the wind is more constrained, okay? So here there is no atmospheric response to the stress. And here we add actually the atmospheric response to the stress, to the new stress calculation. And we see like obviously the stress is more on one side to the other side. So when the stress is higher, the wind is more constrained, the wind diminishes. Okay? And when the stress is actually like decreasing, the wind can blow a bit faster. Okay? So here we still have a negative wind work, but here we have a partial re-energization of the wind. Okay. So this wind work is actually negative. Okay? So that means there is a deflection of energy from the ocean to the atmosphere. What are the results for some simulation? Okay, this is an exercise that Lionel did actually in 2016. We are on the Californian coast, upwelling system, and there is 3 kinds of simulation. Here is like no current feedback. Okay, so we calculate the stress with rho CD wind speed square, no? Here there is current feedback. And here there is a current feedback and the re-energization of the wind, of the atmosphere, as I just explained. And what we plot here is oceanic eddy EKI, okay? So eddy kinetic energy. If we apply the current feedback, we actually reduce our EKI of 55%, which is enormous, right? If we compute also the atmospheric response, so the re-energization of the wind, we decrease only of 40%, okay? So that's why we have called that current feedback eddy killing, because we are decreasing, there is a deflection of eddy field in the ocean, right? So this is a very, very nice result, but this is only for Californian coast, right? And this result has been generalized here. Well, there is like many studies. So there is globally here, it's a paper from Lionel in 2024. There is a damping of the mesoscale activity by 30%. So this is a global map of difference of EKI between a simulation with current feedback and a simulation without current feedback. Okay. So exactly as that one. Okay. And there is many studies. So as I just told you, like 45% of at the US coast. So a paper of Lionel, but also other colleagues, notably CO. 25% of Peru, with a colleague of us, like in Chile, Vera Order. North Atlantic, 27%. 25% for Gulf of Mexico, for Aguilas. And the main idea here to remind is 30% on global, right? So we are dampening our mesoscale activity of 30%. So this is a huge process to take into account, right?
This is without coupling, just using the relative coupling.
This is coupling in a sense, well, so that has been shown with over-coupled simulation, right? And this is coupling in the sense that the stress is computed with the in a relative, yes. So the
Without oasis.
Is with oasis, yes. Yeah. Yeah. Talk about that, yeah. There, yeah. Because you have the partial re-energization of the wind, yeah.
So that one is just currently wind, that one will be oasis kind of situation.
Ah, yeah, when you mean oasis, is like fully coupled or not. Yes, so this can be like prescribed if you wish, but okay.
Subtracted in the.
Yeah, exactly. In the bulk formula. But this is like a fully coupled with wind response, yeah. Okay, some upscaling. So here we see that it's an eddy killing processes. So we damp our mesoscale activity. And what does that mean for the main western boundary current? Okay, so here there is actually a rectification effect or upscaling effect. So control of the western boundary, so by reducing the eddy mean flow. And that tends to stabilize the western boundary current. So here, for example, there is no current feedback. Here, there is current feedback. And what we see here is the main pass, okay, of the Gulf Stream. In black for the simulation, and in orange for the observation, okay? And what we see is that with no current feedback, we are actually two more eddy kinetic energy, and that spread a bit the Gulf Stream path, okay? And here, with the current feedback, we actually stabilize the the Gulf Stream, okay? And our path is very, very closer to the observation. This has been done also for the Agulhas current, and the Agulhas current is very important for the retroflexion, and this is a very challenging thing in modeling. And here we have shown that with the current feedback, we have the retroflexion in a better way. So this is a very important for stabilization of this western boundary current, right? Okay, so this is the oceanic response, large scale, okay, of the current feedback. And there is an atmospheric one. Here, if we come back to the Gulf Stream, we say that we stabilized the Gulf Stream, and the Gulf Stream, you know that all the western boundary current are very important for that because it's a way to redistribute the energy and the heat over the globe, right? Because you have like very, very warm water that goes in very high latitude. So actually, if we rectify our Gulf Stream, we actually, so we with the current feedback, we reduce our like eddy mean flow, and as a rectifying effect or large scale effect, we actually change the mean gradient of SST, okay, over the Atlantic. And we modify also turbulent heat fluxes. That alter actually the troposphere temperature gradient and the baroclinic instability in the atmosphere. Okay, so we are more unstable, less unstable, sorry, if we take into account the current feedback, and we have a stabilized western boundary current and a stabilized Gulf Stream. That leads to less storm track activity, so less extratropical cyclone in the atmosphere. Okay, so finally, this is a very powerful result. Why? Is because from a very, very localized processes, okay, relative wind between the wind and the ocean current, we actually have an impact on extratropical storm, which means that there is an impact on the climate. Okay, take-home message for the current feedback. So it's like a bottom-top effect, contrary to the thermal feedback, okay? Mean that the current feedback modifies the stress and then modifies the wind, okay? And then, so this is the list of what I show like quickly. So current feedback to the atmosphere is has a crucial role in determining the energy exchange, okay? So we have a sink of energy from the ocean to the atmosphere. That means a large dampening of the mesoscale activity. Here I just show that also it's also true at the mesoscale. and there is very, very important rectification effects, upscaling effects, okay? Stabilization of the western boundary current, eddy mean flow interaction, but also precipitation, extratropical storm track, etc. Okay, now I'm going to conclude, finish that presentation to say, once again, so that was my first word, is like, before to run any simulation, we have to set a scientific question, right? It's not good to say like, okay, I'm going to run that, and then, oh, maybe I'm going to see that or whatever, no? The setup of the thing like really depend on the scientific question. So if we are interested into those kind of processes, and we've seen that those RC interactions are also important for the mean state and mean variable for the ocean and the atmosphere. Do we really want to represent all those processes in a fully coupled simulation and do sensitivity tests, etc.? So that depends on the question. Why? Is because also WRF is very demanding. Okay, so it's like 30 to 50 times of computing of CROCO. Okay, so before to launch anything, we might think, okay, because it's very computing demanding. That means that it costs a lot of energy, CO2, etc. So this is not good for our CO2 thing here. So here I propose you just do some strategy. So once again, it depends on your scientific question. But what would be the strategy to take into account thermal feedback or current feedback in a lighter way? Meaning like without the big machine of WRF and CROCO coupled with wave, etc. Well, for thermal feedback, you remember that thermal feedback, there are some processes that induce mixing, okay? So it's very hard to represent that without a model, with a simple parameterization. But what is currently is doing, or what we are doing currently, and what we are trying to develop is actually a very, very simplified and lighter atmospheric model just for the marine boundary layer, okay? 1D or 3D. We are currently actually developing that, and it's on the stage of validation for the thermal feedback processes. Then, what about the current feedback? Okay, for the current feedback, we have seen that the current feedback is super important for the ocean dynamics because it's dampening of mesoscale activity, okay, stabilization of western boundary current. So we really want to take that into account, okay? Do we need to run a WRF, CROCO, like big thing? Not necessarily, because we can use some parameterization. Here, the parameterization like proposed is if we take into account like the surface current in the calculation of tau, we know that our stress is actually the part of the atmosphere plus an anomaly, okay? And Lionel like, calculates that anomaly, and that anomaly is actually linearly dependent to the surface current, okay? So we can evaluate our anomaly of the stress as a function of the current, right? And by doing that, you're gonna take into account, well, parameterized this current feedback. How we do that in the CROCO? There is some CPP key, okay, to define. So here, this is like the two main line. I propose you to see the documentation, section 7 in the documentation, and read the paper of Lionel, 2020, who have done like a lot of experiment to better represent the current feedback into a forced case of ocean model. So that's it. That's it for me. Here, this is like a non-exhaustive list, but the main paper that I discussed in that presentation. I'll give you the slide this afternoon, so I think I'm going to send like an email to you. You already have it? Perfect. And the last slide was actually like a sketch that I've done like in the past to represent like most of the thermal feedback processes and meaning for surface mean flux, etc. So I just put that like this, you have that sketch. So thank you. That's it. So if you have questions, I'm happy to respond. I was a bit long, maybe. Okay.
Si alguien en línea también quiere preguntar. No, aquí eso se escucha. Y ustedes pueden preguntar en español si él responde en inglés. Esa es la regla con Fabien, ¿cierto?
Sí.
Una pregunta. Dale. Pues como quieras.
O en francés.
O en
No.
francés. En francés los demás sí quedamos un poco...
Sí.
No, thank you for your talk. It's very interesting. I was just like thinking about like the heat feedback. So you're talking about like, let's speak of the feedback in the wind, but the wind is right there, right? It's already like blowing. And this is just modulating the wind, right?
Yes.
Okay.
So this is a modulation of the wind when it blows over a front.
Okay. So there's no wind genesis.
Wind.
So if you start from a stable, like non-moving atmosphere, this will make the wind go, right?
True. If there is no wind, there is no response.
Yeah.
True. So that does not generate the wind, but that modifies the wind.
Okay. Yeah. So yeah,
Okay.
doesn't mean you feel like
Exactly. So you have to have a wind like blowing, but you have generation of little structures like a converging divergence, which might be like super important just due to the. But you have to have an existing wind.
Yeah.
This is for sure.
Thank you, Fabien, for this lovely presentation. I'm just wondering if these two options, I mean, the thermal feedback and acoustic feedback, are they comparable?
So yes, for the current feedback. Yes, so current feedback is. I don't know. Okay. There is a parameterization for the current feedback. Okay. So with the first CROCO, you can use the parameterization of Renault et al. 2020. Okay. Which is actually the evaluation of an anomaly of the stress due to the surface current and this linear relationship that is found. For the thermal feedback is way more complicated because that involves like mixing in the atmosphere. So the best thing that we are trying to do is to use a simplified model of the MABLE, atmospheric boundary layer, 1D and 3D. And those models are already developed. And now we are like trying to use CROCO with, implement it in CROCO. And we are on the stage of validation for thermal feedback. So we don't know yet if it's working well or not. Okay, gracias.
Muchas gracias. En este momento vamos a tomar entonces... ¿tú quieres hacer una pregunta? Dale.
Yeah, sure.
Creo que hay un punto muy importante, no alcancé a ver si lo discutieron. Por ejemplo, en Chile nos pasó mucho que la gente estaba haciendo modelos de océano para estudiar remolinos y las larvas de los remolinos. Si uno no toma en cuenta esto, la mitad de los remolinos que hay en su modelo son falsos. Entonces uno calcula trayectorias y dispersión y todo, y sin este eddy killing, la tesis ahí queda así como la mitad verdad. Así que esa es la importancia de tener esta correcta interacción entre océano y atmósfera, porque nos va a afectar la parte biológica, la dispersión de larvas, por ejemplo, el transporte de nutrientes. Así que hemos cometido ese error de no tomarlo en cuenta y uno se entusiasma contando remolinos y variación anual de remolinos que no existen, que existen en el modelo, pero que con un intercambio de energía correcto van a desaparecer.
A la hora de implementarlo en CROCO, pues basta simplemente con activarlo, hay que hacer algo más.
Sí, activar.
Pero hemos cambiando a las ondas. Ahora es solamente SFX-CFD.
Okay, so you have to define that, and if that is defined, that is defined. So yeah, CPDef, well, see the document. I mean, that's the name of the keys in the cppdef.h.
Claro, y la otra activación es cuando acoplas CROCO y WRF a la vez.
When you activate the parameterization, you keep the online copy with Word.
Well, if you do a copying, you don't need the parameter because it's already done. Because you have the WRF.
If you don't want to do that.
Exactly. So this is the case of a forced ocean model. Okay. If you are copying, if you have like a full couple, WRF, CROCO, WaveWatch, whatever, you don't need that parameterization. This is the parameterization for a forced case.
So the couple model must be very helpful.
Yeah.
Wow.
Sí.
Not all of them. So you have to choose between one is N and one is G. And you have to pay for it. And as Fabien said, it's much cheaper to use the condition. What can be used that we want to do, but if you are focused on the ocean side, the parameterization is much easier. In terms of computations,
Yeah. I mean, WRF is like can be like 50 times a CROCO. So it's kind of painful and pollutant as well. So we have to be careful.
Bueno, ahora yo creo que tenemos más preguntas, entonces para los que también estamos en línea, vamos a tomarnos una pausa y volvemos más o menos en 10 minutos.
Ok, muchas gracias.